Alright, today we're talking about Chapter 3, Section 1, using the first derivatives to classify maximum and minimum values in sketch graphs. Alright, so we're going to be talking a lot about the concepts in this particular section before we dive into the actual material. So we have a few pages to dig through to understand concepts, definitions, theorems, and things like that. And then once we get into the actual problems, you're going to see it's not that big of a deal. So if while I am going over the concepts, if there are no cogs spinning in your brain, again, don't worry. We'll take care of it in the end. Furthermore, let me also point this out. I don't know if I actually said this to this class, but um, I always I like to give the notes to students because for me as a college student myself, I always did better in classes where I could just sit there and listen, and then the notes are given to me. All right, as opposed to furiously writing down notes and and then trying to put everything together later on when I'm home. So, uh, there are many people that just enjoy taking notes in the middle of class and then go home and look at them. If that's you, that's your prerogative, no big deal. But I do suggest, at least for this section, to just listen and just absorb everything we're about to go over before you actually start digging in and just taking notes furiously. All right, the first thing we're going to talk about is increasing and decreasing functions. You should be pretty familiar with increasing and decreasing functions. If our function is going up and to the right, we are increasing. If our function is going down and to the right, we are decreasing. Now, we do have a more rigorous, in mathematics, we have a more rigorous definition for that. And the definition, let's see if I think we put all this on the next page. The definition for this would be if we have some function f, and it's increasing over some I, so interval I, then for every a and b, so for every two numbers in our interval I, if a is less than b, and this is what it looks like, a is less than b, going on the x-axis, it's just basically saying like 2 is less than 3, then f of a is less than f of b. Then the function at a, or in this particular case, let's just putting numbers out there, then the function at 2 is less than the function at 3. And that's what that means. And then of course we talk about decreasing. If a function f is decreasing over I, again I is just the name of the interval. We name variables, functions, and intervals. And then for every a, b, and I, if a is less than b, again a is going to always be less than b if we're looking at our x-axis like this. Then f of a is greater than f of b. Then the function at a is greater, right? It's higher than f of b. And so this is just a rigorous definition of an increasing and decreasing function, as opposed to the visual that we have been used to up until this class. Okay, so this leads us to a theorem. I guess I need to put the sense in there, huh? Just try that again. Alrighty, so theorem 1, or rather, let's start in here. Since the derivative of a function f tells us the slope of the tangent line, right? So basically, looking at this, if we have an increasing slope, notice our secant line here is positive, right? And if we have a negative slope, then we have a negative secant line. And this leads us to our theorem. If f is differentiable over an open interval I, then if f prime of x, or the derivative of x, the derivative of f is greater than 0 for all x and I, then f is increasing. And if the derivative is less than 0, then it is decreasing, which makes sense, right? Because again, looking at this particular, these two pictures, I mean, this diagram also shows it, but this one's one we've been working with. If we're going up, okay, notice how the slope of the secant line here, again, like it says, positive, and slope of the secant line is negative. So what we're trying to get at here is when a graph is positive, our derivative is going to be positive, and when our we have a negative slope, we're going to have a negative derivative, right, or a negative secant line. All right, next up, in terms of definitions, we're going to talk about critical values. Now, I may have, well, never mind. I don't think I did in this class. All right, so what is a critical value? So let's look at this graph here. We're all over the place. We also have sharp edges here, more sharp turns, and then we continue going. Okay. Now obviously this is just an arbitrary graph, but let's make a couple notes on this graph. So first of all, f prime of x, all right, the derivative is equal to 0 at c1, c2, c4, c7, and c8. So what does it mean that the derivative is 0? Well, when the derivative of a function is 0, that means that we have simply just a horizontal line, right? Because, well, that's the slope. The derivative of a function is the slope at that point. So at these points, we have a horizontal line. So we see indeed that the derivative is 0. The derivative, f prime of x, does not exist at c3 because it looks like we have a vertical line there. At C3, C5, we have a sharp turn, and C6, we have a sharp turn. Okay, so again, there's nothing much to this graph, just I guess mainly as a refresher. But notice how we do indeed have, zero slopes, no slopes, and then we have the sharp turns. So we're going to define a critical value as a function f. A critical value of a function f is any number c in the domain of f for which the tangent line at c in f of c, so at the point, the critical point, and the function at the critical point, is horizontal or for which the derivative does not exist. So a critical value is just going to be where we do not exist or we have a horizontal line, and that's it. Let's see. If c is a critical value of function f, then c and then f of c is a critical point. All right, so again, critical values, critical points, we're just talking about horizontal lines or where our derivatives do not exist. And then we'll put this over here. All right, so continue the reading process. So thus in the graph of f above, which is going to be this function here, c1, c2, c4, c7, c8 are critical values because their derivatives are 0. c3, c5, and c6 are critical values because the derivative does not exist. And I believe we don't have to read that. And the next concept we're going to talk about are maximum and minimum values. And of course, you know what maximum and minimum values are. You've seen them before, but we're going to figure out a different way to actually find them. I'm going to put this on the notes, but I'm not going to read over it. I don't even think I have room here. Okay. Yeah, let's go back and talk about where we originally snipped. All right, so the whole point of today's lecture is finding maximum and minimum values. So how do we go about doing that? Well, looking at this graph here, we're going to consider this graph with peaks and valleys. So obviously we have, looks like a valley down here, and looks like we're kind of peaking up here, right? Well, that's true, but that's not necessarily all the maximum and minimum values. The relative minimums are going to be basically an area of the graph that's surrounded by, or that's actually, all right, we're talking about minimum, that is surrounded by points that are higher. It doesn't have to be the absolute minimum, right? Notice how we note this particular point to be relative minimum because exactly to the left and exactly to the right of it, the points are higher. Right? This looks like the absolute minimum of this graph, but we still call it the relative minimum for now. But again, that's because it is lower than the 2 points beside it. And again, all these concepts of derivatives are going to come back to us again regarding this because we have our slopes that go to it. The function of, or I'm sorry, yeah, the slope of the function that goes to our maximum and minimum values. Uh, Real quickly, let's see. I want to point out that the plural form of maximum is maxima, and the plural form of minimum is minima. And then we collectively, the maximum and minimum values are called extrema. The singular is extremum. So there's some English for you. Uh, our next theorem, if a function f has a relative extreme value, f of c, on an open interval, then c is a critical value. So what's that saying? Well, if our derivative is equal to 0, uh, well, I'm sorry, we have a critical value if our derivative is equal to 0 or if our derivative does not exist. And again, I know this lecture is very, very, um, honestly, I guess lecture heavy here at the beginning. But once we get into the actual problems, you're going to find out it's not really that big of a deal, and it's a lot easier than you think it would be. I think. All right, so this is our derivative test. Again, we're going to be doing this in practice, so I'm not going to necessarily go over it. All right, and then there's the meat of the lecture. We'll go and snip that and prepare. Alrighty, so um, as I said, this is just going to be, we're actually going to put this into practice, so I'm not going to necessarily go over this chart, but we will talk about the first derivative test for relative extrema. So obviously this is called the first derivative test, so that must mean there has to be a second derivative test, right? And there will be. But for now, for any continuous function f that has exactly one critical value in an open interval ab, right? F has a relative minimum at c if the derivative of f is less than 0 from on a to c, and if the derivative of x is greater than 0 from c to b. So what this is saying, let's see. Well, it's hard to, let me push this to the side. Maybe I can draw this out a little bit better. All right, so looking at our first term here, we're saying that our function f has a relative minimum at some value of c if the derivative of f of x is less than 0 from a to c, and if the derivative of f of x is greater than 0 from c to b. Okay, so here's the way this works out. Let's if we looked at and I'm going, this is kind of counterintuitive, I know, but obviously we have the points from a to b, and then here in the middle we're actually going to put c. I know it seems kind of weird and, like I said, counterintuitive, but that is this isn't actually the first time I've seen this in a textbook. It's just it's a known property that textbooks do. So what we're saying here, right? We're just going to look at f1 right now. It has a relative minimum at c, right? And c is, I guess I didn't have to erase it. C is just going to be some arbitrary number there. If the derivative of our function is less than 0, so that means if it's going down, right? So if our graph is going down, from A to C, and if the derivative is going up is positive from C to B, so we're going up. Okay, so this tells us that this is a relative minimum, which makes sense, right? Makes sense. Hopefully, if I draw it out, it makes more sense than if you just read this this all together. Okay, and relative maximum is going to be, kind of the same thing, but the opposite, and we'll go ahead and talk about that real quick. All right, just kind of cover it, because this is the main concept of today's lecture. We're going to be doing this a lot in the next, I think, four examples. All right, so f has a relative maximum at C, so we're going to have a maximum here at C. If the derivative of our function is greater than 0, so that means its tangent line is going to be going up, right? And if the derivative is less than 0 from C to B, and if it's going down. And again, like I said, it's just the exact opposite of what we saw with the relative minimum. And of course, the last part is f has neither a relative maximum nor relative minimum at C if f prime of x has the same sign. Okay, so again, let's put this all into practice before we get too confusing. So looking at example 1, it reads, consider the function f given by our function here. And I probably should have snipped a little more than that. The problem isn't just consider it. It's a pretty easy problem. Just consider. Okay, so consider the function f given by f of x. Find any relative extrema. So the first thing we have to do to find any relative extrema is we need to first find the derivative of the function. So we must first find the derivative, and this is a pretty easy one, right? Which is there's no lodi high minus high low or anything like that. So f prime of x is going to be 4x cubed. Well, that's going to be 12x squared minus 9x squared. So that's going to be minus 18x. And then minus 30x, which is going to be simply minus 30. And then plus 25, well, it doesn't really matter there. Okay, so that's the first step we have to do. We have to get the derivative. The second step, and let's actually put these in steps. So let me put this over to the side a little bit. Okay, so step 1, we're going to get our derivative. Step 2, what we're going to do is we're going to set our derivative equal to 0. So we're going to have 12x squared minus 18x minus 30 is equal to 0. We can immediately divide both sides by 2, so we can say, we can actually divide by 6. Yeah, we can actually divide by 6. So we're going to say 2x squared minus 3x minus 5 is equal to 0. And then we can factor here. We could say 2x minus 5 and x plus 1 is equal to 0. And then once we set it equal to 0, we're going to find our critical points. So our critical points here are going to be where the derivative of f the derivative of f is equal to 0, and it looks like we're going to have critical points here at x is equal to 5 halves, positive 5 halves, and at x is equal to a negative 1. Okay, so these are going to be our critical points, our critical values rather. So let's do this and say these are critical values. Right, and all I did to get those critical values is take the derivative of my function and then set them equal to 0. The next step we're going to do is something that you've seen before, obviously not in taking critical values, but we've done this before when we solved inequalities. So let's go ahead and make our nice number line here. And was it positive 5 halves and a negative 1? So we'll just put negative 1 here and a positive 5 halves here. Okay, so we're made a number line, and all we did was take our critical values and put them on the number line. Again, 5 halves and negative 1. And of course, I put them, kind of in order, right, from left to right. One moment. All right, sorry about that. I think I caught the super cold that people have been talking about. But anyways, so we have our interval, and looking at this interval, we looks like we have the interval from, and let's actually move this down just a tad. Okay, so we have the interval from negative 1, or negative infinity to negative 1, right? So negative infinity to negative 1. We also have the interval from negative 1 to 5 halves. And then we have the interval from 5 halves to infinity. Okay. So those are our three intervals. And if you recall doing something like this before, what we had to do was we had to choose a number in that interval. And actually, let me fix this. I don't actually usually put the brackets there. Or the braces. I don't know why I did this time. I think it would probably look better like this. Yeah, I have no idea why I put the braces there. That 5 looks like a 3. Still looks like a 3. There we go. All right, there we go. So what I'm going to do is I'm going to choose some number within each one of these intervals in the yellow. I'm just going to choose one of these numbers, and I'm going to put them into my equation. All right, and so what was my first derivative equation? Which was 2x squared minus 3x minus 5. So put this in white actually. 2x squared minus 3x minus 5 is equal to 0. Again, this was my equation I had for my derivative. And I actually don't want it negative equals 0. So I'm going to choose some arbitrary number, but I'm going to choose a number that's small, right? So looking at this interval here, from negative infinity to negative 1, I could choose negative 177, right? But I'm going to have to put that negative 177 into these x's. And I don't know about you, but I'm not really in a hurry to square 177 and then multiply by 2. So I'm going to choose the smallest number I can relative to my interval here. So from negative infinity to negative 1, I'm just going to go ahead and choose the number negative 2. Okay, so negative 2 is going to be my test point. From negative 1 to 5 halves, here's the thing. If you have 0 available to you, always use it. Always use it, right? So I'm going to use 0 for this one. And then from 5 halves to infinity, well, 5 halves is 2.5, so I'm just going to go ahead and use 3 here, okay? So I'm using the smallest number that's available to me in each one of these intervals. And again, hopefully this kind of rings a bell. I know you've done this before with solving inequalities. So what I'm going to have to do is I'm going to take this number and I'm going to plug it into my first derivative. And I'm going to note if it's going to be positive or if it's going to be negative. And that's it. Just note if it's going to be positive or if it's going to be negative. So if when I plug in negative 2, plug in negative 2 into this function, negative 2 squared is a positive 4. 4 times 2, that's 8. And then 8 minus, and then a negative 3 times negative 3 times negative 2 is a positive 6, so that's going to be plus 6, and then minus 5. So 8 plus 6 minus 5, that tells me that it's going to be a positive number. So we're going to have a positive number in this interval. 0, again, I said if you have the option to use 0, always use it. And the reason why is because the arithmetic is so easy, right? This goes away, so it's negative 5. So we have a negative number for the second interval. Oh, I don't know why I shouldn't have done that. And then 3, well, we're going to have to deal with the slash marks there, but we can live with that. So 3 squared is 9, 9 times 2 is 18. 18 minus 9 minus 5, well, that's going to make it a positive number, right? We don't necessarily care what the number is, we just want to, we care about the sign. So looking at this uh, equation, or number line rather, it looks like we're going from I mean, we definitely are, not necessarily looks like, we're going from a positive to a negative, and from a negative to a positive. Now, what does that mean? Well, that is the slope of the tangent line. Okay, so that tells me, and if we go back to this page here, right? All these words that mean very little to you probably told us that we have a relative minimum if my derivative goes from a negative to a positive, and we have a maximum if my derivative goes from a positive to a negative. Well, in this particular case, in this particular function rather, we are going from a positive to a negative and from a negative to a positive. So what does that tell me? Well, it tells me that since I'm going from the first positive to a negative, we have a relative maximum. And since I'm going from a negative to a positive, we have a relative minimum. So we have a maximum here and minimum here. And when I say here, I'm talking about this point. We have a relative maximum at -1 and a relative minimum at 5/2. And let's pull up the graph for it. Was that our function? Pretty sure. One moment. Yeah, that was our function. All right, so again, to really drive the point home, we said that we had the relative maximum at -1, right? Because we went from positive to a negative. We went from positive to a negative. We had the maximum here at -1. There's the max. And then from a negative to a positive, we had the minimum here at 5/2. And if we look at the graph, we do indeed see that here at -1, we have that relative maximum. And here at 2.5 or 5/2, right, we have that relative minimum. And so without even graphing, without even using a graphing calculator or anything like that, we were able to determine the maximum and minimum of a function. And that is pretty handy considering if I wanted, if I were to try to graph this function, well, look, I would have had went down to -40 and +40. It would have been kind of cumbersome, right? And the ideas behind finding maximums, and relative minimums, we're going to see exactly why that's useful here in the coming sections. But this is probably going to be the most useful thing that you've done in mathematics, maybe. All right. I guess I think this kind of goes with example 1 as well. These are just little notes that we have. And then we'll jump to example 2. So find the relative extrema and sketch the graph of the function f given by f of x is equal to 2x cubed minus x to the 4th power. So again, the first step we have to do here is we're just going to find the derivative. And again, since this is just a simple equation, we can just take the derivative pretty easily. So we got what, 6x squared, so 6x squared, and then minus 4x cubed. Right. Next up, what we're going to do is we're going to set this equal to 0. So step 2, we're going to set it equal to 0. 6x squared minus 4x cubed is equal to 0. All right. And remember all those factoring things we had to do before in previous courses that you probably thought, I'm only going to use this for the next week and I'll be done. Bad news, we have to do it a lot. And this is one of those cases. So let's go and take advantage of the space over here. We're going to factor out a 2x squared, it looks like. So 2x squared. And what remains looks like a 3 and then minus 2x. Okay. So this tells me that my x is going to be equal to, I've got an x equal to 0, and I have an x equal to, let's put an and instead of comma there. And x is equal to, looks like a positive 2/3, or 3, yeah, 3/2. Okay, so these are our two zeros, and that's where we're going to begin with our interval. And let's see, how much space did I take up last time? I bet I can put it all here. At least I'm going to try to. I got a bad feeling about this. I shouldn't have done that. Oh well, so we have our 0 here and our 3/2 here. And again, these are just, they're arbitrary. I've seen students in the past, they'll put a 0 here, 1, 2, and there's nothing necessarily wrong with that. It's just, the number line is just there to just kind of construct your thoughts. The Where they're placed, as long as they're placed, accordingly, right? Don't put positive 3/2 to the left of 0. Then they're really just placed arbitrarily. Doesn't necessarily matter. So these are our intervals, and let's go ahead and note. Let's go ahead and note this interval. This is going to be from negative infinity to 0. This is going to be from 0 to 3/2, and this is going to be from 3/2 to infinity. Alrighty, so we're going to have our test points here. So our test point for the first interval, this one, from negative infinity to 0. Again, if you wanted to, you can choose negative 177. Something wrong with that. There's nothing wrong with that. But I like to keep it simple, so I'm just going to choose a test point of negative 1. Unfortunately, my favorite number is already taken. Right? 0, I cannot use that for my interval, but I can use 1. Right? If I can't use 0, then I'm going to use 1 because squaring 1, cubing 1, all that stuff is pretty easy to do with 1. And then 3/2, well, that's 1.5. Well, let's go one above it to 2. So those are our test points: negative 1, positive 1, and 2. And what we're going to do is we're going to plug them into this equation here. Or, I mean, if you wanted to, you can put it into this one. And honestly, I'm probably going to put it into that first one anyways. Yeah, let's go ahead and put it into this one. All right. It doesn't necessarily matter because, as you can tell, I mean, with the arrow there, they're pretty much the same, right? It's just this one is the factored form. Don't really know which one would be easier, but it doesn't really matter. So let's go and do the arithmetic here. We're looking at this equation. So if I were to square negative 1, that'd be a positive 1. So 6 times 1 is just going to be 6. And then negative 1 cubed over here is a negative 1. Negative 1 times a negative 4 is a positive 4. And so we've got a 6 plus 4, which is going to be positive. So this tells me that this portion is going to be positive. Right. Next up, we're going to plug in the number 1. So if we plug in the number 1, makes it pretty easy. Again, looking at this equation. So 1 squared is 1, 6 times 1 is 6, and then 1 cubed is 1, 4 times 1 is 4, so 6 minus 4 is also a positive number. All right, so that's a little change from the last example. All right, and then we're going to plug in a 2. Well, 2 squared up here is 4, 4 times 6 is 24, so 24 minus, well, what is 2 cubed? Well, that's 8. Yeah, 8. 8 times 4 is 32, so 24 minus 32, that is a negative number. Okay. So looking at this particular interval, going from negative infinity to 0, so going from negative infinity, let's put it in red, from negative infinity to 0, we have that positive um, derivative. From 0 to 3 halves, we have positive, so we're going from positive to positive. But then from 3 halves to infinity, we are changing. We're going from positive to a negative. So if we're going from a positive slope to a negative slope, what does that tell us? Well, it tells us we have a maximum at 3 halves. So let's just put next page here. So we have a maximum at x is equal to 3 halves. I think we had to do something else. All right, so it wants us to sketch the graph of the function as well, but I'm not going to. Right. And so we see it on your homework and definitely not on your test. I've looked at your final. You're not going to have to graph one of these from scratch. That's why it's not really a big deal that I kind of hand wave through that one. But notice how at 3 halves we do indeed have that maximum, right? And real quickly, just in case, again we're 37 minutes in, just in case I've kind of lost you a little bit. We're going from a positive derivative, positive slope, to a negative slope. Okay. Well, if I were to just arbitrarily graph a positive slope and then change to a negative slope, we can see that we do indeed have a maximum there. Okay. And one more time. All right, notice going from here, let's look at this from 5 halves, right? We're going from a negative slope, looking at the negative, going from a negative slope to a positive slope. We see that that would be a minimum. And that's all we're doing here is just taking, looking at our intervals and seeing, hey, do we have a positive slope? Do we have a minimum slope? And then, adjust our answer accordingly. Ooh, no room. Okay. Oh, yeah, we got room. We just have to overlap. There we go. All right, so the first two examples are pretty easy to find the derivative, right? Now we're gonna jump into the things that are a little more complicated. But the funny thing about that is, it's kind of like multiplying or adding negative numbers, right? This particular function, at least I know when I was a student, I would see this particular function, I'd be like, oh, geez, well, why can't it just be normal? But we do know that the derivative of e to the x is just e to the x, right? It's nothing too difficult. But e to the negative x obviously is just slightly different because we're taking the derivative of negative x. But hopefully when you see a problem like this, your brain doesn't just shut off. Um, and you're like, hey, I can do this. This is pretty darn easy. G prime of x. I'm actually going to need a little bit more space, so I probably should pull that down a little bit. All right, so g prime of x, we know it's going to be first times the derivative of the second. So we're going to say x squared times the derivative of the second. So the derivative of e to the x, well, again, it's going to be e to the x, but what we're doing is we're multiplying it also by the derivative of my exponent, right? So the derivative of negative x is -1, so it's going to be negative e to the negative x. So first times the derivative of the second plus the second times the derivative of the first, which is 2x. Right. And then let's polish this up a little bit. Looks like we're going to have a negative x squared e to the negative x, and then plus 2x e to the negative x. Right. And from there, we can factor. Looks like we can factor out an x, and then e to the negative x. And what remains looks like it's going to be a negative x plus 2. Okay, so that is g prime of x. Now step 2, we want to set that equal to 0. And lucky for us, this is actually pretty darn simple, right? So we're going to set this equal to 0. So we have e to x, x times e to the negative x times negative x plus 2 is equal to 0. This tells me that x is equal to 0 and x is equal to, looks like a positive 2, right? Because we're putting a negative sign in front of the 2. So that's why it's positive 2. So my zeros are, I'm sorry, yeah, I guess it would be at zeros. The derivative at 0, I guess, is going to be x equal to 0 and x equal to 2. So we're going to proceed like we've been doing so far. We're going to go ahead and make a number line. And hopefully you see now what I mean by, the beginning of this particular section was very, kind of lecture-y heavy, but then we get to the actual computation, and it's not too bad. So anyways, we're going to have our intervals 0 to 2, and they are nice and neat for us. No fractions here, so negative infinity to 0. Unfortunately, we can't use the number 0. I'll be honest with you, that makes me sad every single time, because 0 is just too easy to use. Instead, we're going to use the number negative 1, we're going to use the number 1, and we're going to use the number 3. Right. And shoot, well, I have to bring the equation back. What was the equation? Which one would be easiest to use? I actually think the factored form would be easiest to use. X e to negative x. Okay. And again, all I'm doing is just looking at my the factored form of my derivative. Okay, so what I'm going to do is I'm just going to plug the value in again, and I'm just looking for a positive value or a negative value. Now the question might be asked, well, what if it's 0? Well, as you can tell, I've conveniently never used those values that make it 0, right? The values that make it 0, in this particular case, are 0 and 2, so I'm not going to use the numbers 0 or 2. And of course, you could see that for the previous examples as well. So it's always going to either be greater than 0 or less than 0. It'll never be equal to 0. But anyways, if we plugged in a negative 1. Oh, maybe we have to deal with e's. That's unfortunate. Okay, whatever. So if we plug in a negative 1, let's go ahead and put this. I don't know if I need to use a calculator for this, but I'm going to. So we have a negative 1 times e to negative 1. We got negative 3e. Okay, so negative 3e is a negative number, obviously, I guess. So that's going to be a negative there. Next up, we're going to plug in a 1. Again, using our point here, we're going to plug in a 1 for x, everywhere there's an x. So that should be pretty darn easy. And we just end up with e to the negative 1, which is going to be a positive number. And then lastly, 3 and we're going to have a negative number. Hopefully I put that in right. We'll see when we look at the graph, huh? Alright, so all I did was put this into our equation, and let's actually put the equation up a little bit right here. Alright, so looking at this particular interval, it appears that, well, we're going from a negative to a positive, and then from a positive to a negative, right? So this tells me that I'm going to have two relative extrema, and I'm having a relative minimum and a relative maximum, right? Because I'm going from a negative slope to a positive slope and from a positive slope to a negative slope. So this tells me I'm going to have two extremes, and let's go ahead and put the graph up. There's our test points. All right. So again, we said that 0 was a minimum from a negative. We didn't actually write minimum. We probably should have. Let's go ahead and do that. We have a minimum here at 0, and we have a maximum here at 2. There we go. Alrighty, so, and of course we can see this in the graph, the graph of the function x squared times e to the negative x. We're going down, 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 and then we bounce up at 0, and there's a relative minimum. And then up here, it's hard to tell, but we have what's called, well, we will later find out, it's called inflection points. We have a relative maximum there. And I mean, that's about it. I'm pretty sure we got one more to do. Yeah. All right, so again, step one, we're just going to take the derivative. Now, the derivative of this function, again, we're going to do the chain rule, right? This one's not too bad. But the chain rule, we take the exponent attached to my binomial there and put it out front, right? 2/3, and then what's inside, x minus 2, and then we subtract the derivative, or not derivative, the 1 from the exponent there. So 2/3 minus 1 is going to be a negative 1/3. And then we multiply this by the derivative of the inside. Well, the derivative of the inside is just going to be 1. So this actually just stays the same like this. So thank you, Pearson, for throwing us a little bit of a bone there. Next up, what we're going to do is, maybe I should have, oh no, I don't know if I did that previously. Okay, I did. Yeah, let's go ahead and be more precise with our notation. By let's, I mean me. Let me be more precise with my notation here. Okay, so there we go. All right, next up, we're going to set this equal to 0. Well, we don't necessarily have to set it equal to 0 because it's actually abundantly clear what, or rather, when the values has a 0 derivative, right? And I say it's abundantly clear, but it looks like a jumbled mess right here, right? And that's because it is. But we know that when we have our exponents here, they mean something, right? We can actually fix that up and change it into something that's a little bit easier on the eyeballs. So let's go ahead and change it to something a little bit easier on the eyeballs. So we're going to have a 2/3, right? And then we have x minus 2 raised to the negative 1/3 power. Well, that negative 1/3 power means we're taking the cube root of x minus 2, right? Well, since it's a negative, it means we're going to take it from the numerator, because right now it's essentially over 1, right? We're going to take it from the numerator to the denominator. So it's going to end up looking like the cube root of x minus 2. Right? Let's actually move this 2 over here, put it in the center, make it look a little bit better. Right? So all I did there was, again, just change it from this mess into something a little bit prettier that we're more accustomed to. And then hopefully at this point, it's pretty easy to see when my value here in my derivative is equal to 0, right? And it's not necessarily equal to 0, but it's also where we have what's called our critical point. And we talked about that earlier. Let me see if I can fix up the definition here. That's not it. Critical values. Okay, so looking here, we see that a critical value of a function f is any number c in the domain of f, so any number that we call, any number, whatever, any number c in the domain of the function for which the tangent line is horizontal or for which the derivative does not exist. Okay, so this is a critical value. Up until now, we've had we've done the problems where we have a horizontal line. Okay, we've taken the derivative and found where there's a horizontal line. We found that they're a horizontal line because we set them equal to 0 every single time. We set the derivative equal to 0 every single time, and that told us that that was where we have, well, it's equal to 0. But the second part of that definition also says, or for which the derivative does not exist. So let's go back to our last problem here. And if there's one rule, oh, we've done a lot of notes today. If there's one rule in mathematics that everybody remembers, it's that we cannot divide by 0, right? So if we put a 2 right here, we get a solution that is undefined, right? And that's okay. That still falls in line with our definition of a critical point. So in this particular case, we're just going to use the number x is equal to a positive 2 as a critical point. As a critical point. Okay. And it honestly makes our interval and all that stuff, it makes it pretty darn easy. Because that's one less thing we have to do here. Okay, so again, our critical point is just sitting here at 2. We're going to have an interval from negative infinity to positive 2, and from 2 to infinity. And lucky for us, the number 0 is available, and unfortunately 3. We have to use 3. Okay, well, all we have to do here is look at signs. We don't necessarily have to do the entire arithmetic. So what do I mean by that? So we're looking at this, the derivative. We're going to plug in a 0. Okay, so we plug in a 0 there. Well, my numerator here is a positive 2, so that's obviously going to be positive, right? And then my denominator, well, we're going to have the cube root of negative 2, right? Because 0 minus 2 is negative 2. Well, the cube root of negative 2 is going to be a negative number. The cube root of a negative number is always negative. And then negative times a positive is a negative. So it's going to be positive over a negative. Okay, so again, we don't care what the number is. We just care about the sign. So we have a positive over a negative. So this tells me that this sign here is going to be negative in this interval. Next up, we're going to plug in a 3. Well, again, then the numerator is a 2, which is going to be positive, over, well, 3 minus 1 is 1. The cube root of 1 is 1. 1 times 3 is 3, which is positive. So we have a positive over a positive. So this tells us that we have a positive number. So, again, if we're going from a negative slope to a positive slope, then this must tell me that we have a minimum. Let's move this out of the way. I don't think the YouTube video will show it, but my Zoom session will. Minimum. So I have a minimum here at 2. And again, well, let's see. Yeah, that's it. And again, we're going to go ahead and snip the graph here. And I'm pretty sure, oh, maybe not. I think we have one more example. Oh, wait, no, we don't. Okay. All right, real quickly, though, before we do wrap this up, we found the where our relative extrema are located, and then of course you just plug that value into the original equation. That's intro to college algebra. It's nothing difficult, but something in a textbook that I want to point out. All right, so we don't use calculators too often in this course, uh, mainly because as a student, I know I was constantly broke, and I sure as heck couldn't afford a $120 calculator, which is crazy. I don't know why there's still $120 when I can do literally all of this on a free app on my phone. But if you do happen to have a graphing calculator, um, you're more than welcome to try out this particular part of the section. But like I said, I haven't actually gotten around to necessarily looking at the final exam. I have glanced over it, but I don't think you're gonna have to do any sort of graphing like this on the final exam. So if you don't do it, that's not a big deal. But if you are going into a STEM field, although I don't think this class is necessarily catered towards the STEM field, but if you are going to a STEM field, then go ahead and try out uh, using this with a calculator because you do actually use this calculator quite often. Um, at least I did when I was working at a factory doing this kind of stuff. Anyways, that concludes today's lecture.